Last episode, we built the coffee shop matrix and watched two rational shops drive each other straight into 4, the worst outcome on the board. Both saw exactly the same logic: no matter what the other shop does, discount. So both discounted. Both earned 4 when they could have earned 10. Here is the question that has been sitting there since the end of that episode: is discount the answer game theory predicts? And if it is, why? What makes that sell special when no discount is right there, looking so much better? The concept that answers this is called Nash Equilibrium, named after the mathematician John Nash, who formalized it in 1950. The definition is precise and worth memorizing. A Nash equilibrium is a set of strategies, one per player, where no single player can improve their own payoff by changing their strategy alone, while everyone else holds theirs fixed. That last phrase is the key. Unilateral deviation. One player moves. Everyone else stays put. If you cannot benefit from that move, you are in equilibrium. Let's use that definition as an algorithm and walk it through the coffee shop matrix, cell by cell. Start at the top left. Both shops hold price, both earn 10. Ask, can roast improve by switching to discount while grind stays on no discount? Roast would earn 14 instead of 10. Yes, profitable deviation exists. This cell is not a Nash equilibrium. Move to the bottom right. Both shops discount, both earn 4. Ask, can roast improve by switching to no discount while grind stays on discount? Roast would earn 2 instead of 4. Worse. No profitable deviation. Ask the same for grind, switch to no discount, earn 2 instead of 4. Also worse. Neither player can improve by moving alone. This cell is a Nash equilibrium. The trap has a name now, and a rigorous reason for being a trap. There is a cleaner way to visualize this. For each strategy grind might play, ask, what is roast's best response, the strategy that gives roast the highest payoff? If grind holds price, roast's best response is to discount, 14 beats 10. If grind discounts, roast's best response is also to discount, 4 beats 2. Roast always prefers to discount. Now run the same logic for grind. By symmetry, grind always prefers to discount too. A Nash equilibrium is exactly where both players are simultaneously playing their best response to each other. At discount, roast is best responding to grind, and grind is best responding to roast. That mutual lock-in is what makes it stable. Now consider a completely different kind of game. Two drivers are approaching each other on a narrow road. Each must independently choose a side, drive on the left, or drive on the right. If they match, both left or both right, they pass safely. If they mismatch, they crash. Run the Nash equilibrium check. At left can either driver improve by switching to right alone? They crash. No profitable deviation. At right, same logic, switching alone causes a crash. No profitable deviation. So this game has two Nash equilibria, left, and right. Both are stable. Both are perfectly good outcomes. And game theory, on its own, cannot tell you which one the players will land on. The driving game reveals something the coffee shop masked: Nash equilibria are not always unique. A game can have one, two, or many. Nash proved that every finite game has at least one Nash equilibrium, that is his existence theorem, and it is a non-trivial mathematical result, but he proved nothing about uniqueness. When multiple equilibria exist, something outside the model has to do the work of selecting one. In the driving game, that something is a traffic law. In repeated games, it might be a shared norm or a history of past play. The math tells you where the equilibria are. It does not always tell you which one will be played. At this point, it is tempting to think Nash equilibrium is the final word on what rational players do. It is not. 3 things it does not guarantee. First, efficiency. The coffee shop in E is 4-4, and both players would be strictly better off at 10-10. Nash equilibrium can be, and often is, collectively terrible. Second, fairness. Nothing in the definition says payoffs must be equal or just. An equilibrium where one player earns everything and the other earns nothing is still an equilibrium, if neither can improve by deviating alone. Third, uniqueness. As we just saw, a game can have multiple equilibria, and the theory is often silent on which one prevails. Nash equilibrium is a necessary condition for a stable prediction. It is not a sufficient condition for a good outcome. So we know what a Nash equilibrium is, how to find it, and what it fails to promise. The next question is, are there games where one strategy is so dominant that a rational player would choose it regardless of what anyone else does? No best response calculation required? That concept is called a dominant strategy. And it turns out the coffee shop had one all along. Episode 3. Thanks for watching. If you found Nash equilibrium as surprising as it is powerful, Episode 3 goes further, dominant strategies, and why the coffee shop had an even stronger prediction hiding in plain sight. See you there.